So we're going to talk a lot later about derivatives and their graphs, but I think if I do it just a little bit right now, it's going to help out with some homework. So remember what the first derivative tells you, right? First derivative is the slope of the tangent. Okay. So I have a graph here. So this is my f of x. And I just want to look at, can we decide, just from looking at the graph, where our first derivative is positive or negative? Right? And we're going to do that just by imagining the tangent lines that we would get. So if we start at negative infinity, right, and think about the lines tangent to our function, so by negative infinity, where x is negative infinity, right? So, right, these slopes here are all positive. So from negative infinity to what value, where do we stop having positive, right, tangent lines, positive slopes of tangent lines? Another way to think of positive tangent line slopes is you're walking uphill. So in math, we always walk left to right, so go ahead and hop on your graph. And if you're walking uphill, then the tangent line slope is positive. Right? So it's positive. It keeps being positive until we get to this x value at the top. So negative 3.3. Again, these are x intervals. And well, then what happens? Well, then we start walking downhill. So our tangent line slopes are, right, negative in there. So we're negative between negative 3.3 walking downhill until we get to the bottom. And that x value is 1.3. And then what happens? Well, right, we start walking uphill again. So up here for our positive tangent slope. So again, so the u for union, from 1.3 to infinity. Okay. So where are they zero? Well, they're zero at the top and the bottom, at those resting places where you change from going uphill to downhill. So we have two of those. So one is at x equals negative 3.3, and one is at x equals 1.3. Okay. Now, here's what I want to do. We can't really label our y-axis, but we can label our x-axis, and we can draw a graph of f prime of x. Okay? So we know, right, stuff happens. Our derivative has a 0 at negative 3.3 and at 1.3. It's positive, right, to the left of 3.3. I'm just going to put a plus up here to remind me. And it's positive to the right of 1.3, and then it's negative in between negative 3.3 and positive 3.3. So I just need to draw a continuous function that has these characteristics. I don't know how far down it goes. I don't know if it does other swoopy things in between. But the simplest one I could draw is just a nice parabola. So now let's practice going the other way. Let's say, right, that I have instead a graph of the derivative, and I need to somehow create the function. Okay, so this picture here, this line that we have, is the derivative. So where is my derivative positive? Where are the function values of this derivative positive? Where is f prime of x greater than 0? Well, it's greater than 0, right, whenever you're above the x-axis, and that happens, right, at negative 0.5 to infinity. Where is it negative, right? Where is your function, where is your derivative function below? Negative infinity to negative 0.5. So then where is it 0? So it's only 0 there at x equals negative 0.5. So now we're going to try to come up with a sketch of our function itself. So I know the derivative, so now I'm going to be thinking about when am I walking uphill and when am I walking downhill? Okay, so it looks like everything happens at x equals negative 0.5, and that's where it's 0. So you're going to, right, get to a top or a bottom there. So that's kind of our flat spot. And it could be anywhere, right? We don't know how to label the y-axis, so just arbitrarily pick a spot, right, on where x equals negative 0.5. So we're positive, we're walking uphill from negative 0.5 to infinity. So from negative 0.5 to infinity, we're walking uphill. You could do straight, but probably curved. And then we're walking downhill from negative infinity to negative 0.5. So coming in from the left, we'll be headed down. And I'll draw my arrow up just because we have the ends going off forever to infinity, but right, walking left to right. Okay, and again, that could be anywhere. It could be narrower. We don't really have any labels except for that, that one x value when stuff happens. So just a real quick comment on derivatives and continuity. And the reason why I like to put this here is that it has a logic component in here that's kind of important for a lot of aspects, not just calculus. So let f of x be a function and let a, so a is an x value, be in its domain. Okay. If f is differentiable at a, then f is continuous at a. Okay. So the order of an if-then statement is important because they're not made to go in both directions. Okay. So it's a one-way if-then. The converse, meaning I can't swap them and get a necessarily true statement. Now it might be true, and it actually is true a lot of the times, but it's not guaranteed to be true. Okay, so just because you might have a continuous function, it may not be differentiable. And so the reason why we care about that is because a lot of times we want to find, right, the derivative in addition to giving you the slope of the tangent, it gives you the instantaneous rate of change. So we can only find derivatives if your function is continuous, and then there's another word that we say in math, smooth. So your function has to be smooth and continuous to find its derivative. So here are two examples of functions that are totally continuous, but they're not smooth, right? They have some sharp points in them, right? And these two functions, neither of these are differentiable at a particular value. And both of them, they're not differentiable at x equals 0. They are differentiable at every other x value, but not at that particular value. Okay, and you can look at that one and you can verify for the absolute value function, right? So if we let f of x be the absolute value of x, okay, and if we're just going to look at, right, the slope of the tangent, the derivative from its definition, right? So the derivative, right, is the limit as x approaches 0. I'm looking at that particular value, and then it's f of x minus a is being played by 0, over x minus a, right? Again, being played by 0. So what we have is the limit of the absolute value of x over x as x approaches 0. Okay, that's the definition of a derivative. Well, if we look at that, it's like, okay, well, that looks fine, right? We try to plug in 0, but I get 0 over 0. That's not good. Right? We don't do 0 over 0 yet. So that means I have to look at it maybe numerically. So we're going to look and see what happens as we come from the left and we come from the right. So if we look at the limit as we approach 0 from the left of the absolute value of x over x, and again, you can do this numerically if you'd like, but if we think about it, right, our top is always positive. Our bottom, in this case, if we're coming towards 0 from the left, our denominator is negative, but they're the same value. Top is positive, bottom is negative, but they're the same value. So this actually equals -1. And if we take the limit as x approaches 0 from the right of that, right, ratio, this time, right, top is positive, bottom also positive. I'm doing the ratio, and it doesn't matter how small they get. They don't get to 0, but they can get closer and closer, but it's always the exact same number, top and bottom. So that means that's also 1. Well, these two limits, as I come from the left and as I come from the right, are not the same. So the limit as x approaches 0 does not exist, right? So if the limit doesn't exist, then the derivative doesn't exist. So for a function to have a derivative, it has to be continuous and smooth.